Hi everyone. In today's class we will look at magnetic properties of transition metals, right? In magnetic properties we would be looking at the magnetic behavior of transition metals and ions, right? And when we talk about magnetic behavior, based on magnetic behavior or based on behavior of substances in magnetic field, substances are divided into three categories. First is paramagnetic, when the substance is attracted by the magnetic field. Second is dimagnetic, when the substance is repelled by the magnetic field. The third is ferromagnetic, the substances that are strongly attracted by magnetic field, that is iron, right? Iron is a ferromagnetic substance. So similarly, when we talk about transition metals, right? So when you place transition metals in magnetic field, some would be attracted by the magnetic field, those would be called as paramagnetic. Some would be repelled by the magnetic field, those are dimagnetic. And some are strongly attracted by the magnetic field, right? Those are ferromagnetic, right? Now in this lecture we would be looking into the reason for showing magnetic behavior and reason for showing dimagnetic behavior, right? And then we will prove the same mathematically, right? So let's start it quickly. So substances, we said, are dimagnetic, paramagnetic and ferromagnetic. Similarly, if we talk about magnetic behavior, similarly when we place these transition metals, we would be referring to the first transition series, the 3D transition series, right? So if you place these metals in magnetic field, all these show behavior, or all these show different behavior. Some would be repelled by magnetic field, some would be attracted, and some would be strongly attracted. So right, so let's see the reason for their difference in behavior, right? And then we'll prove it mathematically. So some substances, transition elements, right, are of three types. The first one, those are attracted by magnetic field, right? They are termed as paramagnetic, right? And some are repelled by magnetic field, they are dimagnetic, right? And some are strongly attracted by magnetic field, they are ferromagnetic. Right? Now out of these, which are dimagnetic, which are paramagnetic? Suppose if we place zinc in the magnetic field, zinc would be repelled by the magnetic field, right? So zinc is your dimagnetic. Similarly, if we place scandium, right, Ti, V, chromium, manganese, right, all these would be attracted by the magnetic field, right? So for example, we place scandium, right, or vanadium or chromium, or these are paramagnetic, right? And if we talk about cobalt, nickel, right, or if we talk about iron, all these are ferromagnetic. Iron, cobalt, nickel, because these are strongly attracted by magnetic field, right? Now let's first see the reason, right, for their difference in behavior, right? If we talk about transition metals, right, transition metals, those are attracted by the magnetic field, right? Those are attracted by the magnetic field. They contain unpaired electrons in their n-1 d shell, right? n-1 d orbital. They are the substances or the elements, transition elements, those are attracted by the magnetic field. They contain unpaired electrons in n-1 d orbitals, right? and those are repelled, they contain paired electrons. Right, in d orbitals. To be correct, n-1 d orbitals. n-1 d orbitals. Right, and ferromagnetic contains sufficient number of unpaired electrons because they are strongly attracted, so they contain sufficient number of unpaired electrons. For example, like 4, 3, 2, right? They contain sufficient number of electrons in unpaired electrons in n-1 d orbital. So it is your number of unpaired electrons in d orbitals that will decide the paramagnetic behavior of transition elements, right? More the number of unpaired electrons, more is the paramagnetic behavior, right? And if you have more number of paired electrons, as the pairing increases, the dimagnetism will increase. For example, we said that zinc is dimagnetic in behavior. When we say paired and unpaired, let's first understand what does that mean. We said that in n-1 d orbital, right, you have unpaired electrons due to which they are paramagnetic, right? If you look at 3D series, in 3D series, the d electrons are in 3D orbital, right? It has total 4 shells, so n-1 d here, n-1 d would be your 3D. So number of unpaired electrons in 3D orbitals in case of 3D series will decide the paramagnetic behavior. For example, if you look at first element, right, it has 1 electron in the 3D orbital, right? As you come down, you can see that the number of unpaired electrons will increase till the middle of the series. As you move down, the number of paired electrons will keep on increasing, right? Let me just show you. If I talk about the first element, we know that d subshell has 5 orientations, right? So you have 5 orbitals, 5 d orbitals in total. 1, 2, 3, 4, right? So if we talk about this one, the first element, it has 1 electron. If we talk about second, it has 2 electrons in the d orbital. This is how we will fill. First we will fill each orbital, right? Then we will start pairing the electrons in each orbital. This is how we do electronic configuration. If we talk about third, it has 3, right? If we talk about chromium, it has 5, right? If we talk about manganese, it again has 5, right? And chromium has exceptional configuration because 1 electron, we have done this before, 1 electron from s orbital will jump to d orbital, so that it can result into stable electronic configuration. You have maximum number of unpaired electrons in d orbitals, right? This is exception configuration, right? So here, when you have maximum number of unpaired electrons in d orbitals, in this case, in this series 5 can be the maximum number of unpaired electrons. In each orbit, by unpaired we mean in each orbital you can see you have only 1 electron. So this is unpaired electron, right? So 1, 2, 3, 4, 5. Not 4, this is also 5, this is also 5, right? So you have 5 maximum unpaired electrons, right? So this represents your paramagnetic behavior. Now I said that as you come down, the number of unpaired electrons will decrease. So when the number of unpaired electrons will become less, the number of paired electrons are increasing, right? That means paramagnetic behavior will go down and dimagnetism will go up, right? So if we talk about this 3d6 iron, you have 6 electrons in d orbital. So 1, 2, 3, 4, 5, 6th electron will go and pair up in the first orbital, right? Similarly, if we talk about cobalt, it has 7 electrons, right? So 7th electron will pair up in this orbital, right? Similarly, if we talk about nickel, it will pair up in this orbital. So what is happening? number of unpaired electrons is decreasing as you move towards right in the series, right? This is like the series is going like this. I have written in column, but it is in row, right? So as you move towards right, the number of unpaired electrons are decreasing and the number of paired electrons is increasing, right? So if you look at this, if you look at nickel, electron will pair up in this orbital. If you look at copper, electron will pair up in this orbital, right? So here you have all the d orbitals paired up, right? You have paired electrons in all the d orbitals, right? So zinc corresponds to this. We said that zinc is dimagnetic because it has this configuration corresponds to 3d10. You can see you have 10 electrons, right, corresponding to zinc. 10 paired electrons, 10 electrons where all are paired up, right? You have paired up electrons in d orbitals, right? So this configuration represents your dimagnetic behavior, right? Example is zinc, right? And this configuration where you have unpaired electrons, this represents your paramagnetic behavior. Right? For example, manganese, if you look here. This is clear? So magnetism is due to, or the paramagnetism is due to the number of unpaired electrons in d orbitals, right? And when these substances are placed in magnetic field, they are attracted by the magnetic field, right? And these are repelled by the magnetic field because it contains all paired electrons, right? I hope this is clear. Now there is a way we'll prove this mathematically, that we said that as the number of unpaired electron increases, the paramagnetism will increase, right? We will prove this mathematically also. But before we prove that mathematically, we have to look into one important concept, right? That firstly, how unpaired electron will create magnetic field, right? Because when you place these substances that have unpaired electrons in magnetic field, it is attracted by the magnetic field. We need to look into the reason why it is attracted by the magnetic field. And when zinc that has this electronic configuration is placed in magnetic field, it would be repelled by the magnetic field. Now why it is repelled by the magnetic field, we'll look into the reason, right? But before that, we'll just look into small concept, right? This dimagnetic and paramagnetism can be measured using Gauss balance. Gauss magnetic balance, we call it Gauss magnetic balance, right? What we will do is, you take the substance, take the element, measure it first in the absence of magnetic field, right? Then measure it in the presence of magnetic field, right? And then see if the weight has increased or decreased, right? Now in case of paramagnetic elements, weight will increase, right? Whereas in case of dimagnetic, weight will decrease, right? Because in case of paramagnetic, elements will interact with magnetic field. They will interact with magnetic lines of force, right, in the magnetic field, right? So their weight will increase. Whereas substances that are repelled by the magnetic field, they will result into decrease in the weight, right? Because they are repelled by the magnetic field. So Gauss balance can be used to check if the given element is paramagnetic or dimagnetic. If the weight will decrease, right, after entering magnetic field, it is dimagnetic. If the weight will increase after entering into magnetic field, it's a paramagnetic, right? I hope this is clear. Now let's quickly look at the concept wherein we will prove how the number of electrons will increase the paramagnetic behavior, and how does an unpaired electron will generate a magnetic field that will make it attract in the magnetic field, right? Since we know that if we talk about any atom, any element, right, this is the nucleus, right, and these are your shells, right, where electrons are moving, right, electrons are revolving around the nucleus. This is the nucleus. There are two motions that electrons undergo: orbital motion, right, where these electrons are moving around the orbits. Second is spin motion, right. We know that from atomic structure, we know that electrons spin around their own axis, right. So there are two motions. Let me just rub this off. First is orbital motion, right, because electrons are revolving around the nucleus, right. Electrons have two motions: orbital motion, right, and second is spin motion, right. And these two motion will create magnetic field in a particular direction, right, which will interact with the magnetic field, and the substance will get attracted in the magnetic field, right. Now orbital motion is due to electrons revolving around the nucleus, right, and spin motion is due to electron spinning in if this is the electron will spin in a direction, right. It's like rotating like this, it's rotating like this also, then it's rotate like this also, right. So this is rotating in one direction, right. Say in this direction it is rotating. If this is the electron, it is spinning, right, that means it is rotating like this, right. So when it is rotating like this, it is actually not rotating, I'm sorry, it is spinning. It is spinning around its own axis, this electron. So when it spins, it creates magnetic field, right. So due to orbital motion you have magnetic field, due to spin motion you have magnetic field, right. And why due to orbital motion you have magnetic field? Because if you look at this is an electron. When an electron is moving, right, it's like a charge is moving. We know that whenever a charge moves, it creates, it's like an electric current. Moving charge constitute an electric current, right. So when you have electric current due to this electron, right, we know that electric current produces magnetic field, right. That is why this electron, moving electron, has magnetic field, right, due to its motion, right. So due to orbital motion, since it is moving, it has magnetic field, right. So if it has magnetic field, it has a magnetic moment. Magnetic field, due to magnetic field, it has a magnetic moment denoted by mu L, and it is also spinning around its own axis, right. Since it is spinning, so that will also produce or create a magnetic field. When it produces a magnetic field, that means a moving charge, it also produces an electric current, and electric current produces a magnetic field, right. So when it is spinning, right, because it is spinning or it is revolving, a moving charge will always produce, or it constitutes an electric current, and when you have electric current will produce magnetic field around it, right. So due to orbital motion and spin motion, you have magnetic field, right. So orbital motion, due to orbital motion you have magnetic field, right, due to which you have magnetic moment, right. Similarly, spin motion also produces a magnetic field, and you have spin magnetic moment. This is orbital magnetic moment, this is spin magnetic moment, right. So these two motion will create a total magnetic moment of the electron, right. So your total magnetic moment would be spin plus orbital motion. Due to spin and orbital motion you have magnetic moment, right. Now this magnetic moment is given by your L plus 1, nu L is given by L plus 1, and this is given by S plus 1, right. So this is given by, it is actually, this is given by, this magnetic moment is given by 2 S plus 1, right? I hope this is clear. And this is measured in Bohr magneton, right? This is measured in Bohr magneton. And right, and both these are measured in Bohr magneton, and Bohr magneton is your, it's EH upon 4 pi mc, right? M is the mass of the electron, right, and c is the speed of light, right? I hope this is clear. This is just a formula, a mathematical formula, right? Now we will replace, this is actually Bohr magneton, right? So here we will write it like this: L plus 1, right, plus 2 S plus 1, right? Common in both these is Bm, Bohr magneton, right? Now we need to look at one thing, that this would be 0, right? I'll write it over here. L is equals to 0. This, or what we say is that magnetic moment due to orbital motion is 0, right? This is not much significant, so this term would be 0. So magnetic moment would only be due to spin of the electron, right? It would be due to spin of the electron. So nu would be 2 under root s plus 1 s. Same, I've taken s here. This. Now why this is 0, L plus 1, why this is 0? Magnetic moment due to orbital motion is 0, right? Why it is 0? Actually, if we talk about any transition metal ion, right? Transition metal ions, if this is your metal ion and if you have ligands around it, if it forms a complex, you have ligands around it, right? That donates electrons to this transition metal, right? And you have these electrons orbiting in the penultimate shell, in the 3D shell, in this case, in case of 3D series. So the orbital motion, right, is suppressed or decreased. It's suppressed by these ligands, by these interacting ligands, right? So since the orbital motion is suppressed by these ligands, this term, right, magnetic moment due to orbital motion will be 0. Nu L would be 0, right? Because this motion, right, this motion is suppressed by the surrounding ligands. If this motion is suppressed, right, that means it will not constitute electric current. This is not moving, or if it moves very slowly, very less current or no current, right? Very less current or no current means it will not, no current means it will not produce magnetic field. No magnetic field means no magnetic moment, nu L would be 0, right? And the other one, the spin. So this magnetic moment will be due to spin of the electron, right? It is only due to spin of the electron. So unpaired electrons that are spinning in one particular direction, they will produce magnetic field in one particular direction, right? So it has magnetic moment, which is nu S, right? Which is this, right? Now we know that value of S is equals to half. We know this from atomic structure, right? This is for one electron, right? Value for S for one electron is half. If you have n electrons, then the value of S would be n into half. It would be n by 2, right? So if you place n upon 2 plus 1, n upon 2, right? What you will get? You will get the formula as n plus 2 Bohr magneton under root right? This is in under root. So this is the formula for magnetic moment of unpaired electron, right, which is due to spin of the electron, right? So magnetic moment is the spin only, we also call it as spin only magnetic moment, right, because it is due to spin of the electron, right? And magnetic moment due to orbital motion is suppressed by these surrounding ligands. The orbital motion is suppressed, so magnetic moment would be zero, right? Because no motion means no electric current, no electric current means no magnetic field, no magnetic field means magnetic moment is zero due to orbital motion. So this is your nu is equals to n plus 2, where n is the number of electrons, number of unpaired electrons, right? N is equals to number of unpaired electrons, right? And you can see as the value of n will increase, nu will increase, right? So if you take n is equals to 1, nu has certain value. If you take n is equals to 2, the value of nu will increase. If you keep increasing the value of n, the magnetic moment will increase, right? Magnetic moment will increase, that means its paramagnetic behavior will increase, right? The magnetic field that it will produce due to its spin will increase, right? That is what it means. So as the number of electrons, unpaired electrons will increase, the value of magnetic moment will increase, right? So more the value of magnetic moment means it's creating a strong magnetic field, so it will interact strongly with the magnetic field, right? External magnetic field. I hope this is clear. Now what about paired electrons? Why paired electrons, let me just rub this, why paired electrons are repelled by the magnetic field, right? Now one thing we know from this explanation, that magnetic moment is due to spin of the electron, right? So if you have this situation, right, if you have this situation where electrons are paired up, right, you have these two electrons, right? We are taking the pairing case now, and now this electron will spin in one direction, this electron which is spinning in up direction it is spinning, right? So it will produce magnetic field in one direction, right? And the other electron which is spinning in downward direction will produce magnetic field in one direction, right? Which would be opposite to the magnetic field created by this electron, right? So this electron will create magnetic field which is equal and opposite to this to magnetic field created by this electron, right? So net magnetic field would be zero, right? If this is zero, then your this would be zero, right? Your magnetic moment would be zero, right? Magnetic moment zero means you have no this is not producing any net magnetic field. Net magnetic field is zero, right? When net magnetic field is zero, because magnetic field created by one electron, right, which is spinning in one direction, would be cancelled by magnetic field created by other electron which is spinning in opposite direction, right? Magnetic field would be equal and opposite created by other electron, so its net magnetic moment would be zero. No magnetic moment means no magnetic field. So such substances, because their net magnetic moment is zero, would be repelled by the magnetic field, right? So this is the explanation why electrons that have paired elements that have paired electrons like zinc are repelled by the magnetic field. I hope this is clear, right? Similarly, these electrons, when the number of unpaired electrons increases, the paramagnetic behavior will increase because the net magnetic moment increases, right? I hope this is clear. And for ferromagnetism would be shown by those substances like iron, cobalt, nickel are ferromagnetic that have sufficient number of unpaired electrons.